Okay, so this is Monte Carlo integration. What you can see that I have laid out here is I have an integral, and I've graphed that integral on the first quadrant. The origin is in the lower left-hand corner, and I've boxed this function in between 0 and 3.5 on the x-axis and between 0 and 1.5 on the y-axis. When we do Monte Carlo approximation, the first step is to constrain our bounds in both the x and y direction and create a box around the area of concern. The idea with Monte Carlo integration is I'm going to perform what we call randomizations or random picks of x and y coordinates. It's similar to throwing darts at this red box I've defined with respect to my function. And if I throw enough darts at this red box, I can add up the total number of darts that I have after innumerable throws, and the number or the ratio of darts that has landed underneath the curve versus the total number of darts will give me a ratio that I can then use to extrapolate the area of the red box. So it looks like this. If I have total of 12 randomizations or darts thrown at my red box for my function, and 9 of them I've tested are below the function, that's a ratio of 3 to 4. Well, that same ratio of the area of the red box is going to lie beneath the function or the curve. And so here's the area of my red box, 3.5 by 1.5. And I multiply this by the ratio I calculated from my randomizations. And I get from this calculation an approximate area, 3.94. So obviously when we do this in a computing environment like Excel or MATLAB or whatever, we don't actually have darts. So what this looks like when I plot various steps of the randomization, it looks like this. Here's the function with no random picks, just the regular function plotted on the bounds that I'm concerned about. And after 30 or so picks, some points start showing up, and I keep picking more and more points until I have a sufficient number where I have determined that the accuracy of the randomization will give me a representative area underneath the curve. So what you see here is 87,500 randomizations. And what I do with that number looks like this. Total of 87,500 darts were thrown, but 71,958 of them were tested to be below the function. That's a ratio of 0.824. If I multiply this by my total area, 0.824 by the area of my box, I get an approximate area of 4.326. That's this area underneath my curve. The actual value of the area underneath this curve is 4.32172. Okay, this is the working document for Monte Carlo integration. This is sort of the finished product, or something that your deliverable will resemble. You will be building yours from an empty spreadsheet, so yours may look different, but the outcome should still be the same. Now, what I'm going to do here is I'm going to press the F9 key, and that's going to toggle Excel to recalculate the spreadsheet. You can sort of see my computer's churning a little bit because I'm recording a screencast and computing 100,000 or nearly 100,000 cells. So, but by pressing the F9 key, I'm calling Excel to recalculate every single formula in there. So why is it changing? It's because I'm using a random number generator in these cells. And so every time you recalculate, it re-randomizes all of the numbers. Now, you can see that I have my function plotted over here, and this function is actually being plotted from random outputs in my f of x column. And I have my important sort of vital information here. I have my delta x, which is something we've become familiar with. That's showing up here. I currently have it set to 0.1. And I have my lower bounds, a, and my upper bounds, b. And my index is telling me how many randomizations I have. And my maximum y is the height of my box. So the width of my box is going to be determined by the difference from my a and b, and the height of my box I'm simply going to specify. What's happening now is I'm only using a delta x of 0.1, so the number of randomizations I'm using is only 35. You can see how that's set up here. So after this point, there is no more random points being chosen. That's why my approximation is so far off. You see, every time I press F9, the approximate area changes. 35 points. So by increasing my delta, I now have 3,500 randomizations being used, and my area is 4.3635, which is much closer and much better reliability to the true area. By retoggling the random, you see that this stays much more stable. If I increase this again, I now have 35,000 points. And you can sort of see the pattern here. Now what happened here is I went over the number of cells that I have programmed. I do not have 350,000 cells, and so the area got really funky. So you have to sort of pay attention to how many cells you have programmed, and I believe I can go that far. Yep. So I have 100,000 cells programmed. This particular delta x gets me up to 87,500, and I have a very good approximation for my area underneath this curve. So how does this all work? If you sort of see, if I go down to the very end here, Control End takes me to the very bottom of my sheet, and I have 100,000 cells. I'm going to show you a sort of something you can do to help really big spreadsheets like this out when you need to drag formulas down. So what I'm going to do is I'm going to click on the entire row. I'm going to back off the bottom of my table a little bit. I'm going to click on the entire row, and I'm going to press Shift Control Home. And what that's going to do is it's going to select all of the rows in my sheet from that point up. I'm going to back off a little bit. What I'm going to do is I'm going to hide all of these rows. Right click and then hide. So what you can see, what I have here is I sort of collapsed my table into something that I can actually navigate pretty readily. So if I need to drag a formula down, I can do that without having to go the whole way down my table. You can see Excel is rendering those calculations. Hopefully your computer is faster than this. And that's how we can sort of handle a spreadsheet that's large. Okay, what you see in this table is the function. You can see I just simply use the actual function in this particular column and drag this down through my table, and it's feeding off of the C column. And then what I have in this column is this is my test. So what I'm doing is I'm testing if this particular random y variable is greater than my function. If this number is bigger than f of x, then it's going to put a 0. But if it's under the curve, it puts a 1. So you can go down and see 1.31582 is above the curve, and so my test column marks it with a 0. At the end of the day, I can determine the number of points that are below or above my curve, in this case below, by simply summing up the f column. This tells me the number of points that are below my curve. And going back to the original presentation, I can then determine from this number the fraction of my area constrained by my bounds here that is below the curve. So let's look at a few commands here. Let's look at the rand command. What the random command is, this will generate a number between 0 and 1 randomly. So if I press F9, you see this number will always be between 0 and 1. But I need to get random numbers that are between 0 and 3.5 for my x coordinate and between 0 and 1.6 for my y coordinate. So how do I scale a number that's between 0 and 1 from the random number generator and make them fit those bounds? That's sort of your first programming challenge. Your second programming challenge is to look at this column for the test. How can I tell, or how can I write a test function that will look at this particular value and see if the y value is above or below it? So this is the random number command. And I want to make sure everyone understands a basic if statement. So in understanding any of these commands, what you can do is, there's a couple of ways to navigate this, but under formulas, you can go under logical, navigate to if. And then this will bring up a dialog where you can go to help on this function. It will show you the syntax of this function. You can read about this. But under this, there's logical test. And under here, there's a link to comparison calculation operators. This is an important little dialog box. It shows you how to do comparisons in Excel. It shows you how to determine if two numbers are equal, greater than or equal to, or not equal to. So I'm going to write this by hand, and I'm going to make up two values. I'm going to say 2 and 3. Put them in different cells, and what I'm going to write is if this cell is equal to this cell, then say yes. Otherwise, say no. So here's my basic if statement. So 2 is obviously not equal to 3, especially as I have that if statement written. But if they're the same, the if statement will return yes. So, going back to the original task, how can I create a test to determine if this value is greater than this value? And then I will populate that with, I want to write a 1 if it's below the function. That way when I sum all of those up, I know exactly how many points are below my curve.